Welcome to Lecture 1.6, Limits Involving Infinity. So we've been looking at limits, calculating limits as we're moving towards understanding how to figure out instantaneous change. And the last concept around limits is looking at limits involving infinity. And the first concept is about infinite limits. And this is when, as a function approaches a specific value, as x approaches a specific value, the function actually branches off to infinity. As you can see from the graph at the bottom here, as we're approaching 0, the y value, or the functional value, is heading to infinity. We can see that if you look at the graph or at the table, the limit as x goes to 0 does not exist. Remember that a limit exists if it goes to a constant value. And because this is just constantly increasing, we say that the limit doesn't exist. But again, we can also see as we're getting closer and closer to 0, the y value, or the functional value, is getting larger and larger, and it's going to infinity. So we can actually write that the limit as x goes to 0 of 1 over x squared equals infinity. Now this is a little bit confusing because both of these statements are sort of correct. The first one is a little bit more accurate, that the limit doesn't exist. The second one kind of implies that the limit does exist because it equals infinity. But remember, infinity is not a number. So what this is really telling us is that it doesn't converge. The limit doesn't exist. And so the second equation here, where it says it's equal to infinity, is really expressing the specific way that the limit doesn't exist, and that is specifically that it's going to infinity. Remember, we had one of the discontinuities was an infinite when a function would go to infinity, okay, or negative infinity. So be careful of this. Your homework will ask you to find limits, infinite limits, and so it will ask you to write whether this goes to infinity or negative infinity instead of saying it does not exist. So be mindful of that. I don't really like this because it's the first answer is actually technically correct. D and E does not exist. The second one is really explaining why it doesn't exist, and it is good though for you to figure out is it going positive or negative. Okay. So here's our definition of this. The notation, the limit as x goes to a of f of x equals infinity. It simply means that the values of f of x, remember f of x stands for y, can be made arbitrarily large as we please, by taking x sufficiently close to a on either side of a. Okay, and so the graph here is also explaining this as we get closer and closer to a, our y value, or our function value, is getting larger and larger. Okay. We can also apply the same kind of concept to one-sided limits. For example, in here we have the four one-sided limits x as x goes to a from the negative direction. Both of these are, approaching x from the negative direction. So this first one is graph A here, right? That as we approach a from the negative direction, f of x is going to infinity. And we can see here the third one is we're approaching a from the negative direction, and f of x is going to negative infinity. So this is graph A, this is graph C. And then we can also approach a from the positive direction. In here we have the graph B, because as we approach a from the positive direction, it's going to infinity. And the last graph D is as we approach a from the positive direction, the function is going to negative infinity. Okay. Now note that all of those are possibilities of asymptotes, and specifically vertical asymptotes. and that is part of the definition of the vertical asymptote, is that as x approaches a specific value, the y value goes to infinity or negative infinity. Okay, so we say that a line x equals a is called a vertical asymptote if it meets any of the following statements that we just went through. Okay, that the full limit goes to positive or negative infinity, or any of the one-sided limits go to positive or negative infinity. So let's look at an example. Some of your homework for this section will be very conceptual, and including some of the questions that you'll see on the first test will also be conceptual. And that means you need to kind of figure out what's going on. So notice this first one. We're trying to figure out what happens as x approaches 3 from the positive direction and the negative direction. Well, if x is 3, we can see that the denominator becomes 0 and it's undefined. So now we have to kind of conceptually think what's happening as we approach 3 from the positive direction and 3 from the negative direction. All right, so let's look at the positive one first. So notice if we're approaching 3 from the positive direction, this means that x is going to be a number greater than 3. Greater than 3. So let's say, for example, we might have 3.1. 3.1 minus 3 is going to be a positive 0.1. So we're going to have, and the numerator will always stay positive because we're approaching a positive number. X is close to positive 3. But notice the denominator in this first one is also positive, and it's getting smaller and smaller and smaller and closer to 0. So remember, when you divide a big number by a small number, let's say 100 by 1 or 1,000 by 1, it's a big number. So what's happening in this first set is that that as x is getting closer and closer to 3 from the positive direction, the denominator stays positive, although it's getting smaller and smaller and smaller, so the quotient is getting larger and larger. So we're heading to positive infinity. Okay? Notice when we switch this up, when we approach when we approach 3 from the negative direction, this means we're approaching 3 from smaller values of 3, or values smaller than 3, excuse me. So, for example, x might be 2.9, 2.95, 2.99, etc. Notice all of those values make the denominator negative. 2.9 minus 3 is negative 0.1. The numerator, again, will stay positive because 3 is positive. This doesn't say approaching negative 3. It says approach 3 from the negative direction. So we're going to have a positive over a negative, and so what's going to happen here is we're going to be approaching negative infinity. The denominator, again, is going to be getting smaller and smaller and smaller, so we're dividing this number, which is getting closer to 6, by a smaller and smaller and smaller number. And so that it is going to, and again, positive divided by negative is negative infinity. So on these kind of problems, some of these you're just going to have to use your intuition and think about what's happening as we're getting closer and closer to those values. Okay, the next one. Let's find the vertical asymptotes of tangent x. Okay. So typically when we're looking for vertical asymptotes, we're thinking of rational equations. Remember, ratios, quotients, fractions. So thinking back to trig, how can we write tangent x as a ratio? Well, remember the tangent equals sine over cosine. Okay? And typically vertical asymptotes happen when the denominator equals 0, because this, remember again, this is what's not allowed, and so it's undefined there. And typically as the denominator is getting closer to 0, then we're heading to positive or negative infinity. So there are potential vertical asymptotes where the cosine of x equals 0, or that's where they're happening at. And remember that cosine equals 0 when we're at pi over 2 or 90 degrees, or negative pi over 2 or what's that, 270 degrees, okay, or negative 90 degrees. Okay, remember the 4 quadrants, thinking of the Cartesian system, x and y's is sine and cosine, that, or excuse me, cosine sine, x and y. So x is 0 when we're on the vertical axis. Okay. So we know that the limit of as x goes to pi over 2 from the negative direction gives us that the tangent equals infinity, and because again what the sign here, and then as we are approaching pi over 2 from the positive direction, we're going to get negative infinity again because of the signs as we're getting closer there. So these are our two what am I saying? These are our two vertical asymptotes, and remember that all the trig functions are periodic functions, so it's every pi over 2 interval apart. So we get 0, pi over 2, 3 pi over 2, etc. Okay. We're also looking for, okay, so those were what we called infinite limits. Okay, so infinite limits are when we approach a specific x value, the y value becomes infinity or negative infinity. Okay, that's infinite limits. Okay, infinite limits, when we approach an x value, the y value becomes extremely large or extremely small, negative infinity. Okay, these are vertical asymptotes. Now we're going to look at limits at infinity. Okay, so limits at infinity is when we set x to infinity or negative infinity. Okay, so before we were looking at specific constant values of x where y went to infinity. Limits at infinity is when we set x equals positive or negative infinity. Okay, so let's see what happens when we look at a function. These can be a little bit confusing because notice what happens here is that we basically have infinity over infinity, because as x becomes infinity, infinity minus 1 is still infinity, infinity plus 1 is still infinity, so it becomes a little bit hard to see what's going on. If we look at a table of values for this function, we can see as x gets larger and larger, what's happening here is we're getting closer and closer to 1. Okay. If we look at the graph here, we can see quite clearly that what's happening as x goes to infinity on the right side of the graph, that the y value is equal to 1. And as x goes to negative infinity, y is equal to 1 as well. And so we say here that we have a horizontal asymptote at y equals 1. Okay. So by definition, we say if f is some function over an interval that goes to infinity, the limit as x goes to infinity of f of x, if it equals a constant, means that the values of f of x can be made as close to L as we keep making x being sufficiently large, either positive or negative infinity. Okay. Now remember that the symbol infinity doesn't represent a number, but we still use it in our notation, and so we say the limit of f of x as x approaches infinity is L. These are just different ways of saying that. You can read through them. As x becomes infinite, as x increases without bound because it's going to infinity. All of those are fine examples. Okay. There's many ways that this can happen too, and I want you to see these different pictures of a graph. We can cross horizontal asymptotes, which is unlike vertical asymptotes. You can't cross them because that's where the function is undefined. But horizontal asymptotes you can cross, and you can even see here at the end, this is an oscillating, decreasing function, and so it is again converging on L. All three of these are converging on L. So we have horizontal asymptotes in three very different types of graphs. Okay, and then if we do have that limit, if the limit as x goes to infinity or negative infinity does equal a constant L, then we call that L, that value of L, the horizontal asymptote. Be very clear here too that remember that vertical asymptotes are equations defined as x equals a number. Horizontal asymptotes are defined as y equals a constant number. You will need to remember that and input equations into some of your homework problems. It's very important as you're going through this that you pay attention to how you enter answers in WebAssign. You don't want to get answers marked wrong because you said the horizontal asymptote is at 1, when you should have put the horizontal asymptote is y equals 1. Remember these equations. A horizontal asymptote is a line, so it's not at 1, it's at y equals 1 or whatever value. Okay? So look at this graph and see if you can figure out where the horizontal asymptotes are. You can pause now for a second and see if you can figure that out. Notice this function has actually two asymptotes. The first one is at y equals 2. As x goes to negative infinity, the function is getting closer and closer to y equals 2. As x goes to positive infinity on the right side of the graph, we have another horizontal asymptote at y equals negative 1. So there can be multiple horizontal asymptotes. There can be multiple vertical asymptotes. In fact, vertical asymptotes can even be more than 2. Typically, you would only see a possible 2 horizontal asymptotes. So here we have a graph. It's not easy to see the x and y axis, but they are labeled with the arrows and a little x. So here is our x-axis. Here is our y-axis. See if you can figure out what the infinite limits are, what the limits at infinity are, and the asymptotes. Really hit pause now and see if you can remember those just from this brief lecture. I'm going to continue on, but it'd be a good idea if you could hit pause and see if you can know what each of these are vocabulary-wise, and then find them on this chart, on this graph. Okay. So first, remember, infinite limits are vertical asymptotes. Infinite limits are vertical asymptotes. And this is where, where does y go to infinity? Where is y going to infinity? Okay? Or negative infinity. This should say plus or minus. So notice we have a positive infinity here, and this value is x equals, looks like negative 1. Right? We also can see that here y is going to positive infinity and negative infinity at another place, and so we actually have two vertical asymptotes. We have one at x equals negative 1 and one at at x equals 2. Again, be very clear that vertical asymptotes are equations of lines and is stated as x equals. The vertical asymptotes are not at negative 1 and 2. They are at x equals negative 1 and x equals positive 2. Now remember, limits at infinity, these are horizontal asymptotes, and these are trying to find, does the function go to a constant value of y when x goes to positive or negative infinity? So if we're looking at a graph, we're going to look to the far left for negative infinity. We're going to look to the far right for positive infinity and see what happens. And here we can see for negative infinity, the graph is crossing, or the y value is at 2. And for positive infinity, when x is over here to the positive infinity, we can see that y is equal to 4. And so again, we have two horizontal asymptotes and two vertical asymptotes. All right. So up here we have kind of a rule of thumb, and it's a very intuitive thing. I think it's pretty easy to see that if x is going to infinity, and we have 1 over x, or 1 over x to the n can be anything. It could be any positive integer, I should say. So even if it's x to the 1, notice that 1 over infinity, or 1 over infinity squared, is 1 over a large number. You can think of this kind of like your chances of winning the lottery. 1 in 200 million is pretty damn close to 0, right? And so both of these, if we have 1 over x, or 1 over x to a power, and x is going to infinity, these equal 0. Now what these will help us do is they can help us evaluate limits at infinity for equations. Okay? So notice as x is going to infinity, we have 3 times infinity squared minus infinity minus 2, all divided by 5 times infinity squared. plus 4 times infinity. So it's very confusing what's happening here intuitively. We can't tell, is the numerator growing faster, is the denominator growing faster? If the numerator is growing faster, then it's going to go to infinity. Notice if the denominator is growing faster, it's going to go to 0. So we don't really know what's happening in ratio here. And if they're growing at some kind of constant ratio, if the numerator is growing 3 times faster than the denominator, then we'll go to a constant. So using this, what we're going to do is we're going to multiply each term in the numerator and each term in the denominator by 1 over the largest power of x that's in the denominator. We're going to multiply the numerator and the denominator by 1 over x to the largest power in the denominator. So what that means is we're going to multiply the numerator. Notice the largest power of x in the denominator is a 2. So we're going to multiply the numerator by 1 over x squared, 1 over x to the power of 2. We're also going to multiply the denominator by that, because we have to multiply both the numerator and the denominator by the same thing so we don't change the equation. Because 1 over x squared divided by the same thing, 1 over x squared is equal to 1. So we're really only multiplying by 1. So we're multiplying the numerator by 1 over x squared, and we get this. We're multiplying the denominator by 1 over x squared, and we get this. And notice what we can then do is divide each of these terms by x squared. So 3x squared over x squared gives me 3. X over x squared gives me 1 over x. 2 over x squared gives me 2 over x squared. And I can do the same thing with the denominator here. Okay, and get this. Now, why did we do that? Well, remember when we have the limit as x is going to infinity of each of these pieces, if we have 1 over x or 1 over x to a power or a number over x to a power, it doesn't even matter. It's still going to 0, even if it's not 1. This could be any number up here. Okay? And so also remember that when we have the limit of a quotient, we can take the limit of the numerator over the limit of the denominator. When we have the limit of sums and differences, we can take the limit of each piece. So we can apply that limit to each of these pieces, and notice again, 0, 0, 0, 0. So all 4 of these pieces become 0. And remember, the limit of a constant is just that constant. So here we get 3 minus 0, etc., 5 plus 0 plus 0. And so this actually equals 3/5. You need to know this rule that when you're evaluating a limit as x goes to infinity of a ratio of 2 polynomials, this is a simple way to kind of solve it algebraically. A lot of stuff that we're going to do in calculus, or not a lot, but some of the stuff we're going to do in calculus, I always call it relates to a video game or a virtual game. And that is sometimes you just have to try things and see if they work out. And we're going to see another problem here in a minute, actually right now. So what you want to do when you have a problem like this, notice that if we plug in infinity, we get infinity squared plus 1, which is basically infinity, minus infinity. So we get infinity minus infinity, and we don't know what that means. Is it actually 0? Is it something else? So we have to figure out another way algebraically to solve this problem. What I want you to think about when you're doing these is think about patterns. What did we do before when we would have a radical minus a constant or something? What are some things that we would do to solve radical problems? Well, one of the things we'd often do is multiply by conjugates. Now we cannot simply multiply this function by a conjugate because we're changing the function. But we could multiply both the numerator and denominator. Now there isn't a denominator here, but we could put it over 1 by the conjugate radical. And when you normally see these radicals like this, that's often a good thing to try. So let's look and see what happens when I do this. So if I multiply my original function by the conjugate of the function, and again, notice I'm really multiplying by 1. So this should be in the numerator over 1. So then we get, remember we'll have a sum and a difference up top, which gives us the square of the first term, x squared plus 1, minus the square of the second term, x squared, all over the denominator, because this is the only thing that's down there. All right? So notice what I have now is I have 1 over x squared, the square root of x squared plus 1, or 1 over infinity squared plus 1 plus, there's my mouse, plus infinity. Well, notice this is all positive now, so it's just getting bigger and bigger. I've got infinity plus some more, so this is even larger than infinity. And what do we know when we have 1 over infinity? That it equals 0. Okay? So on these problems, you're going to have to kind of figure out some tricky things, and you can't intuit through them. You're going to have to use some algebra, and you're going to have to use some algebra tricks that are just look like what you've done before. Okay, so let's look at example 10 here. Now again, we've got infinity squared minus infinity, which would seem like it would still be infinity, but we can't just take the limit of both parts. Because infinity is not a number, the rules for limits don't exactly apply. Okay, so it would be wrong to write this as the limit of x squared minus the limit of x. Again, because infinity is not a number, so the limit laws don't work there. But notice we can factor this. So x squared minus x equals x times x minus 1. So we get infinity times infinity minus 1, which is still a positive number. So we basically have positive infinity. Okay. Here we didn't know, it looks like we might have had 0, but we couldn't quite tell which one was going bigger. Here we could kind of see that. Again, this is kind of an intuitive problem. If infinity squared is going to be a lot more than infinity. Okay. Now what about the second one? Again, we can factor out an x up top, and we already saw that and the top is going to be infinity, right? And down here we have 3 minus infinity. So we're going to have a negative in the bottom. But notice here what we have as well is a polynomial over a polynomial. So if we multiply the numerator and the denominator by 1 over the largest power of x in the denominator, that means we're going to divide each term by x. So x squared by x gives me x. X divided by x gives me 1, and that's what I see here. 3 over x, I've got that here, and minus x over x gives me minus 1. And remember, this goes to 0, so what I have is infinity plus 1, which is infinity, divided by negative 1, so it goes to negative infinity. So this is kind of using the polynomial rule. It's also using some intuition, and you probably could have intuited this as well, that 3 minus infinity is going to be a negative number, and then you could have factored that. All right. So, of course, as we've been looking at this, there are precise definitions for limits and infinity. So the first one is looking at infinite limits. And this is, so notice, because the y value is going to infinity, we're only going to have one of our constraints here, and that's the delta. Okay? And this is just saying that at some limit, at some proximity close to a, that the function is going to be above a value of m. So it's going to be sufficiently large. Okay? Also notice that here, these are limits at infinity, and this again is giving us, now we're looking at the epsilon, and I don't think it's epsilon again. Sorry, I don't know this Greek letter. But this is some constraint that it's close enough to L, plus or minus this epsilon, and at that point, the x value is going to be greater than n. Okay? Now, if you're doing any of these problems, and I'm sorry this is a little bit late, and hopefully I said it in an earlier lecture, and if you're trying to calculate what the deltas are or the epsilons are, and you get two different values because the graph is not symmetrical. Here they look exactly symmetrical for the definition reasons. But this delta might be larger than this delta here. When you're asked to find a delta that meets the definition or an epsilon, always pick the lower value. And think of it like this, that if, let's say you're building a bridge, we always say that with engineers, and part of it is about the constraints that you want on the bridge, about how strong it is. And so these limits here, these ranges, you want the smaller limit because you don't want to give more leeway in that bridge strength, right? You want it to be as strong as possible, so you're going to use the smaller range. So in any of these definitional limit problems, if you have multiple deltas, pick the small